Okay, so I'm sharing my screen. Are you able to see?
Yes, sir.
Okay, you can see. Thanks. Yeah, it's also getting recorded, I believe. Let me just quickly check. Okay, yeah. Okay, so let's start with basically today's session and NPTEL session. So there's a 9TA session, and this is on principles of signal systems. And my name is Yashvanth, and I'm from IISc Bangalore. Okay, so part one is going to be on summarizing the week 9's lecture, where basically the lecture started with some problems on filter design, right? So in filter design, the kind of problems that we encounter is that you analyze the frequency response of a particular system and analyze how the rate at which the frequency response decays to zero, right? So depending on that, you have the notions of what is called the bandwidth of a system. And again, you will characterize the roll-off factors, that is the rate at which the frequency response goes to zero. So those are the kinds of problems that we have seen in the class on filter design. The other kind of problems that professor had discussed was problems concerning RC circuit. So if there is a circuit with a resistor and a capacitor, then it will have its own oscillation period. Okay, and slowly, eventually, it will come to a steady state. It's a transient state, and then followed by a steady state. Okay, so associated with any RC circuit, you're going to have something called the time constant. That is basically it tells you the time required for the circuit to reach a state which is at least 63% of the final value of the steady value that the system can achieve. Okay, and it has a specific expression. What is the time that it takes to achieve that? It's precisely given by T equal to R times C, where R is a resistance and C is a capacitance. Okay, and similarly associated with this circuit, there's something called the 3 dB bandwidth. Okay, so similar to it, this basically you can think of it as a low pass filter. Fine. So any filter will have a bandwidth, as I told previously, and you can measure the 3 dB bandwidth of an RC circuit as omega naught equal to 1 by RC. Okay, so that was I've just given the key formulae. So, but the main focus or the main conceptual part of this week started with something called the sampling of a continuous time signal to obtain a discrete time signal. Okay, so let's say there is basically what does sampling mean? So let's say there is a continuous time signal x of t. I'm plotting this as a function of t, and you have a signal to vary something like this. Okay, now in practice, I have any system. Okay, in practically, if I want to design a system, it might not be able to process a continuously varying time signal, right? So it will have its own for example, own resolution, right? Every chip will have its own resolution. For example, it can only process a 4-bit data or 16-bit data or or maybe 128-bit data and so on and so forth. So basically, it can only process a discrete set of data, not in continuum, right? Similarly, you cannot process the data which is continuously varying over time, but rather discretely varying over time. So that basically motivates to study discrete time systems, discrete time signals in more depth, right? So if I want to understand how does a discrete time signal look like, basically I need to obtain these discrete time signals from a continuous time signal via the process called sampling. Okay, so this process of obtaining discrete time signal from the continuous time signal is called sampling. Okay, sampling a continuous time signal to discrete time signal. So what you do in sampling is basically you only take the data of the signal at regularly spaced intervals. For example, let's say TS is refers to something called the sampling time. Then every TS, so at 0 you measure the sample, then next at TS you measure the sample, at 2 TS you measure what is the amplitude of signal, at 3 TS, at 4 TS, and so on. Okay, and you just sample, just get the values at these samples, sample the time indices. That is basically your these discrete time signal value. Okay, so basically you get x of n, which is defined as small x of nts. That is, for ts is a fixed number that you choose, and x of nts will be denoted as x of n. So now you see this is basically a discrete time signal because it is not for any time. It's only defined for a specific amount discrete values of time. Okay, so this is basically called sampling of a continuous time signal to get a discrete time signal. Okay, so now let's say Ts is a sampling time. Then basically you can define Fs to be as equal to 1 by Ts, that denotes a sampling frequency of your signal. Okay, so 1 over Ts is the sampling frequency. Now, how do I do the sampling? Mathematically, how do I get discrete time signal from a continuous time signal? Mathematically, how do I represent? That is represented by something called the impulse train sampling. Okay, so basically what I do is I define something called an impulse train. Okay, I think this is very familiar to all of us because we have been seeing impulse train for long now. Okay, in our sessions. So basically in impulse train sampling, what you do is you have an impulse, you define your impulse train something like this. Okay, that is summation over several delta functions. See, I mean summation over several delta function which are Ts apart in the time domain. So you see, this is your time axis. Let me just draw it. So this is pictorially represented here. This is your time axis. Okay, and then you basically have delta functions at every instant in time. At every once in Ts, sampling interval once in Ts. Okay, and this basically it's a periodic signal. So this is called an impulse train. Okay, now what I do is I multiply my or given continuous time signal x of t with this impulse train. I multiply both these signals. Then the resultant signal, all right, resultant. So if, for example, if I go back, if I take this continuous time signal and if I multiply with this impulse train, I will get this particular discrete time signal, right? So, but that is basically the mathematical way to capture the process of sampling via the impulse train sampling. So if you do this multiplication, you can show that your expression is x ts of t equal to summation k equal to minus infinity to plus infinity x of kts times delta of t minus kts. Okay, so sampled signal is represented as x subscript ts of t, where ts represents the sampling time that you have chosen. That is under our control. Okay. Now, once I have sampled my signal, I want to analyze what is the Fourier spectrum of the sampled signal. That is, what is the Fourier transform of small x of ts of t? What I'm interested, that is denoted by capital X of ts of omega. Okay. Now, there is a nice relation between the Fourier transform of your sampled signal and the Fourier transform of your original signal. Oh, your original signal is x of t, sampled signal is x ts of t. There is a nice relation between the Fourier transform of x of t and Fourier transform of x ts of t. Okay, that is given by this expression here. So what this expression says is the Fourier transform of your sampled signal is nothing but summation over 1 by ts times summation over k equal to minus infinity to plus infinity x of omega minus k omega s, where x of omega is a Fourier transform of x of t and xts of omega is a Fourier transform of xts of t. Okay, so essentially if I want to draw this, if I want to understand what this means, okay, I'll give you an example and explain here. So let's say that my x of t is my, let's say, a sinc function, something like this. Okay, that is my given continuous time signal. Now we know that the sinc function has a Fourier transform, something like this, rectangular signal. Correct? In the frequency domain, it's just a rectangle or something like this. But now let's say I sample my x of t to obtain x ts of t at at every ts time interval. Okay, then I get this signal. Then if you write down the Fourier transform of the sampled version, what it says is it is basically given by this particular signal written in brown color. So what is the relation between x ts of omega and x of omega? The relation is that xts of omega is a periodic version of x of omega. That is, you repeat the frequency spectrum of x of omega multiple times. It's a completely periodic signal. It is never-ending signal. So here, if you see, it is just this much, but xts of omega keeps on repeating. And what is the period of the periodic such repetition? Exactly equal to the sampling frequency omega s. That is given by 2 pi by ts. Okay, of course there is also a small change in the amplitude. So instead of 1, the 1 get multiplied by omega s, but that's just an amplitude shift. But more importantly, you get multiple replicas which get repeated along the frequency axis. Okay, and this is precisely captured by this equation. So essentially what it says is the Fourier transform of a sampled signal is a periodic version of the Fourier transform of the given original continuous time domain signal. Okay, is it clear? I mean, just confirmation, is it clear? Because this is very important going forward. I can't hear, but can you please?
Yes.
Yeah.
Okay, sir. Okay, sir.
Okay. Okay. Great. Yeah. Thanks. Thanks. Okay. Now, basically, okay, this is the property of sampling of signals. Now, suppose if these replicas, let's say these are different replicas, right? Now, suppose if they overlap on each other, it's possible that these can overlap on each other because what is the period of this signal? Omega s. And omega is something that we choose. If we choose omega s to be a very small number, then it's possible that these two boxes can overlap on top of each other. Okay, and this particular phenomena is called the spectral aliasing. Okay, so aliasing means a high frequency component, for example, this is at a high frequency component, comes and appears as a low frequency component. That is, when it overlaps, the high frequency appears as low frequency component, right? That phenomena is called spectral aliasing. Okay, if you want to avoid spectral aliasing, let's say that this is, for example, this is my original x of omega, but this is a replica, the next replica or image of your original x of omega, right? If I want these two boxes to not overlap, okay, then what I need to have? I need to have this gap between these two boxes to be non-zero quantity. What does that mean? So you see, I told the period of this signal is equal to Fs, that is the sampling frequency. Now this, okay, let me just write it down. So now Fs minus, what is this gap? This is nothing but W. Okay, let's say W is the maximum frequency of your x of omega. Now this is also W. Okay, then what is this width? Fs minus 2W. Correct? Fs minus 2W. Okay, and now if I want to avoid spectral aliasing, that is, if I want this distance to be non-zero, then this Fs minus 2W should be greater or equal to 0. What does this translate to? This translates to the condition Fs is greater than or equal to 2W. Okay, so whenever Fs is greater than or equal to 2W, where W is the maximum frequency content of the signal, your the Fourier transform of your sampled signal will not have the spectrums overlapping on top of each other. Will have no overlaps. Okay, so in summary, to avoid spectral aliasing, the required sampling frequency is, you should have the sampling frequency of the signal must be at least 2W, where W is the maximum frequency content in x of t. Okay, now, okay, so now what did we do? We saw what is sampling, how does sampling affect the Fourier transform. Then we introduced the notion of spectral aliasing, and we told that what is the condition to avoid spectral aliasing. This is what we have told till now. Now the question is, why is spectral aliasing important? I mean, why is no spectral aliasing important? Why are we saying that we should not have spectral aliasing? What is so important about this condition Fs greater than or equal to 2W? Okay, so to understand that, let's see a small demonstration. Suppose your sampled signal xts of t, that is your time domain sample signal, okay, is basically given to you. Someone already gave you the sampled time domain signal, and somehow from the sampled signal I want to recover my original signal x of t. Okay, how do I do that? How to do that process? That is, see, if you in the left the input, someone has already given me my sampled version. So this, all these discrete time sample domain sample signal already someone has given me. Question is how to basically get an equivalent continuous time signal from given this discrete time signal. Okay, that is the question. One solution is I know that the Fourier transform of this continuous sampled signal will be the periodic version of the continuous time signal. Correct? So let's say solution is, let's say something like this I have. Okay, these the blue boxes are the the different replicas of your replicas of your the original Fourier transform of your original signal x of t. Now what I do, I apply, let's say, a low pass filter. Okay, if I do a low pass filter, then what happens is everything outside the box will be eliminated. Only signal inside this box will be passed in the output of the low pass filter. So the output of a low pass filter will be only the original signal. I mean, only the first box. The other spectrum will not be there. Now, what does it mean? So you see this black box, I mean, sorry, this blue replicas of blue boxes, it basically corresponds to sample is a continuous time signal. But the moment I put a low pass filter, it only has a single box whose inverse Fourier transform will be the continuous time domain signal. Okay, so in some sense, if you just apply a low pass filter of over the sampled signal, you will be able to recover back your continuous time signal. Okay, that is the key. That is, if I want to convert back my discrete time sampled signal to a continuous time signal, then I need to apply a low pass filter. Okay, I need to apply a low pass filter. Now, if I want to recover this first the primary or the fundamental box here, the output without any distortionless. Okay, I want to recover distortion in a distortionless manner. Then what is the condition? I should not have these secondary blue boxes should not come inside your low pass filter box. Correct? Otherwise, what will happen is this frequency will also come inside this red box, and that will distort your actual x of t. This is precisely the reason why your replicas should not overlap. Okay, if they overlap, then essentially you have distorted your actual signal. Okay, you have essentially not the sampled signal will no longer be representing the original continuous time signal. It will be a distorted version of a continuous time signal. That's why we should avoid spectral aliasing in general. Okay, you should avoid spectral aliasing in general. So that gives rise to this result, which is called this Nyquist sampling theorem. Very important and fundamental theorem. Okay, what it says is any continuous time signal x of t can be sampled and reconstructed back from its sampled signal without any distortion if the sampling frequency fs is greater than or equal to 2 times fm. Okay, or in angular frequency w omega s more than equal to 2 omega m. I didn't finish, where fm is the maximum frequency component of x of t. Okay, this is called the Nyquist sampling theorem. Very important. So this basically gives you a benchmark of what is the minimum sampling rate. See, the general is rule of the minimum sampling frequency must be at least 2 times the maximum frequency of the signal. Must be at least 2 times. Okay. Now, any signal is said to be sampled at Nyquist rate if I set the sampling frequency to be exactly equal to 2 omega or f is equal to 2 f. Okay, so until now, is it clear? Hello? Until now, is it everything clear? Am I audible? Are you able to hear me until now? Hello? Okay, you can hear me, right? And you can see my screen also. Okay, fine. I hope. Okay. Yeah, fine. Thanks. Okay, so that is basically called Nyquist rate. Okay. Now, how does the reconstruction happen? Basically, what we have told here is that I have my sample signal. I need to put a low pass filter and get my original x of t. But mathematically, what does it mean to pass it through low pass filter? Okay, low pass filter. Remember, what is the inverse Fourier transform of a low pass filter? A sinc function, because it's a rectangle in time frequency domain will give rise to sinc linear time domain. Correct. So and moreover, low pass filter means you're multiplying the spectrum of your xt of omega and the spectrum of your low pass filter. You're multiplying frequency domain. So in the equivalent time domain, they will basically have convolution. They will have convolution, and that is precisely you see in this equation. Okay, you can recover back. That is your actual continuous time domain signal, which is recovered, called as xr of t, is equal to convolution of, that is the term is convolution of your sampled signal and the sinc function. Why sinc function? Because low pass filter's impulse response is a sinc function. And why convolution? Because I'm doing a product of the Fourier transform of sampled signal and the low pass filter's response. Since I'm doing product in the frequency domain, the time domain will have a convolution. Okay, and that is precisely your expression for recover your continuous recovered continuous time domain signal x of t. Okay, so this is the process of sampling a continuous time domain signal and then recovering the continuous time domain signal from its sampled version. Okay, so then the main takeaway from this concept is the Nyquist sampling theorem. That is, if I want to do a distortionless sampling and a recovery, the sampling frequency must be at least twice the maximum frequency content in your x of t. Okay, that was the first part of the this week's lecture. The second part of this week's lecture was dealing discrete Fourier series. Okay, so now once I have sampled my continuous time domain signal to get a discrete time domain signal, now what are the properties that I can analyze on the discrete time domain signal? So just like how we had Laplace transform, Fourier series, Fourier transform for a continuous time domain signal, for discrete time domain signal, you have Z transform, um, uh, discrete Fourier series, discrete time Fourier transform, and another is something called discrete Fourier transform. Okay, Z transform is something that we already discussed. Now, this week we will discuss discrete Fourier series. That is the Fourier series defined for discrete time signals. Previously, we discussed for continuous time signals, a Fourier series for a continuous time signals. Now it's a discrete time signal. Again, Fourier series for a discrete time signal is defined for a periodic signal, periodic discrete time signal. Let's say x of n be a discrete time signal with period n naught. Then, very similar to the continuous time Fourier series, your discrete Fourier series can be, it says that your x of n can be represented as a finite summation of complex exponential terms. So this e power j something is called a complex exponential, CE, complex exponential. And you sum over several such complex exponential weighted by appropriate coefficient Ck. Okay. One main difference between a discrete time series and a Fourier series and a continuous time Fourier series is, in continuous time Fourier series, this summation was an infinite summation. If you remember, we had k equal to minus infinity to plus infinity. But for a discrete Fourier series, is a finite summation only from 0 to n naught minus 1, where n naught is a period of the signal x of n. Okay, and specifically you will define where k ranges from k omega naught, where k ranges from 0 to n naught minus 1. Okay, so this is basically your discrete Fourier series. And given I mean if you want to represent discrete Fourier series, I need to know what is my Ck, right? Ck is basically given by this expression. Cl is equal to 1 by n naught summation n equal to 0 to n minus n naught minus 1 x of n e raised to minus j L omega naught small n. Okay, if for example, if you put L equal to 0 here, then this becomes 0. So e power 0 is equal to 1. So it's just summation of 1 by n naught summation n equal to 0 to n naught minus 1 x of n, which is nothing but the mean of the signal. It is the average of the signal over one period. N naught is a period. So over one period of the signal, I'm computing the mean, the average of the signal. That is captured by C naught. Okay. Sometimes the C naught is also called DC component of x of n. DC component. Okay, now about convergence. DF, the discrete Fourier series, is always guaranteed to converge because of the finite summation. But whereas if you recall Fourier series, we gave conditions called Dirichlet conditions, which are sufficient conditions. For example, it should have finite discontinuities, finite maxima, minima, absolutely integrable, those kind of conditions we gave because it was an infinite summation, and infinite summation was used to define a Fourier series. But here everything is a discrete summation. See, this is a discrete summation. Again, this is also a discrete summation. So this discrete summations always converge. So the discrete Fourier series is always guaranteed to converge. Next, some few properties, just 4 properties in particular, which Professor had discussed. Okay, first is called the periodicity of your discrete Fourier coefficients. Okay, what it says is your Ck plus n naught is equal to Ck for all k. Okay, that is your discrete Fourier coefficients are also periodic. Okay, for example, what I mean is, let's say n naught equal to 4. Okay, then basically what it says is C5 equal to C1, C6 equal to C2, C7 equal to C3, C8 equal to C4. Now, if you want to go back to C9, that is again same as C1, then C10, C11, C12, again C13, and so on. So essentially, if I am just able to compute C1, C2, C3, C4, I know the C values for every other number. Okay, that is called the periodicity property of your discrete Fourier series. Next is a duality property. Okay, what is duality property? Similar to your Fourier transform duality property only. Continuous time Fourier transform. So if x of n has a discrete Fourier series coefficient C of k, if I construct a discrete time signal using C of k as a time domain, and the corresponding DFS, the discrete Fourier series coefficient, will be n naught scaling times x of minus k, where x is the original signal that you have taken. It's very similar. The structure is very similar to that of your continuous time Fourier transform duality property, except that there is a small scaling by n naught, where n naught is the period of the signal. Again, following discrete continuous time Fourier series properties for any real signal, any real discrete time signal, the Fourier series coefficient Ck follows conjugate symmetry. That is, C minus k is equal to Ck star. Star is a conjugation operation. Finally, the Parseval's relation that says that summation k equal to 0 to n naught minus 1 mod of Ck square equal to 1 by n naught summation n equal to 0 to n naught minus 1 mod of xn square. That is basically, again, the interpretation is that energy remains constant in time and frequency domains. That is the interpretation of your Parseval's theorem. Okay. Are there any questions? I think this is a good time to ask the question if you have anything. Okay. So I guess everything is clear. Someone can just again confirm so that I know that my internet is still on and you're able to hear me. Okay, so I'm not able to hear from anyone, but let's go ahead. If in case there's some confusion, please ask me. So the question is, this is the question 1. An ideal minus pi by 2 uh, phase shifter, okay, is defined by the frequency response h of omega equal to e power minus j pi by 2, and if omega is greater than 0, and e power j pi by 2 if omega is less than 0. Okay, so that is basically, for example, if you want to represent, if you have an input x of t, this is a system which basically does minus pi by 2 phase shifter, and the output is y of t. Okay, so this impulse response is h of t, whose frequency response is h of omega given above. Okay, so this is called a phase shifter. That is, it shifts the phase of your input signal by 90 degrees, minus 90 degrees. Okay, that is called the minus pi by 2 phase shifter, and its impulse response, its frequency response is given by this h of omega. Now the question is, first question, find the impulse response h of t of this phase shifter. Number two, find the output y of t when x of t equal to cos omega naught t. Okay, this is the question. Okay, so the question is, find the impulse response h of t of this system. In other words, I'm asking you, what is the inverse Fourier transform of h of omega? Okay, let's do solution. Okay, so let's simplify a bit. So what is e power minus j pi by 2? It's nothing but cos minus pi by 2 plus j sine minus pi by 2. Okay, so this is nothing but 0 minus j equal to minus j. Similarly, e power j pi by 2 is what? Cos pi by 2 plus j sine pi by 2, which is nothing but 0 plus j equal to j. So if you go back and see this h of omega, I can simplify this h of omega as implies your h of omega equal to minus j if omega is greater than 0, minus j if omega is greater than 0, and plus j if omega is less than 0. Okay, now this is nothing but minus of j if omega greater than 0, minus j if omega less than 0. Correct? Minus of this number. Now, can anyone recognize what is this function? It takes a value, some constant value when omega is greater than 0, and it takes the negative of that constant value for negative omega axis. What is this function? Yes, can anyone tell me what is this function? Yeah, guys, am I audible? I mean, are you able to hear me well? Okay, let me just tell you this answer. Just tell if this is okay at least. Minus signum function of omega. Of course, minus j times signum function of omega. Is this clear? Minus j times signum function of omega. Okay, this basically your given h of omega, therefore is equal to minus j times signum function of omega. Now I have to find the inverse Fourier transform of h of omega. Now this is easy because in the previous sessions we've already found out what is the inverse Fourier transform of signum of t. Right? Now what you will do, we apply duality property. Okay, so recall your signum of t in time domain, its Fourier transform is what? 2 by j omega. 2 by j omega. Fine. Therefore, this is something known to us. Okay. In other words, by duality property, if I have 2 by jt, that is, if I take the time domain version of this signal, then its Fourier transform will be 2 pi times signum of minus omega. Correct? That is my duality property. But I know that signum of minus omega is minus signum of omega. So this is nothing but minus 2 pi signum of omega. Okay. So that is 2 by jt. It's nothing but minus 2 pi signum of omega. But what do I have? I have just minus j signum of omega. I need to find the inverse Fourier transform of minus j signum of omega. But I have minus 2 pi signum of omega. Okay. That implies first let us kill the 2. That means 1 by jt has the Fourier transform minus pi signum of omega. Just linearity property of Fourier transform. Now kill the pi. How to kill the pi? Just divide by pi on both sides. So it's nothing but 1 by j pi t has the Fourier transform minus signum of omega. Now what is this is same as this except for a j term. So multiply by j on both sides. If I multiply on j both sides, I get 1 by pi t has the Fourier transform minus j signum of omega, which is equal to the h of omega that is given in the question. What does this mean? This means that impulse response of h of above system is h of t equal to 1 by pi t. Now, from previous classes, can anyone recognize, have you ever seen this impulse response of a system to be 1 by pi t anywhere before? Did you see any kind of system like that? Yes.
Could not remember, sir.
Yeah, okay. So if you remember, this is, do you remember this Hilbert transform?
Yes, sir. Yes.
Yeah, so for Hilbert transform, any Hilbert transformer will have the impulse response to be 1 by pi t. Okay, so the main takeaway from this question is that uh, any system that does a minus 90-degree phase shift is nothing but a Hilbert transformer. And Hilbert transformer is basically a 90-degree phase shifter. It will phase shift the input of the signal by 90 degrees and then gives that as an output. Such that any 90-degree phase shifter is called a Hilbert transformer. Okay. So that is about Hilbert transform. Now the question, this is about the first part. Find the impulse response of impulse response h of t. Second part is find the output y of t when x of t is equal to cos omega naught t. Okay, so this is simple. So the second question, y of t is equal to what if x of t is equal to cos omega naught t. Okay, now what we will do is we will go by frequency domain approach. That is y of omega is equal to x of omega into h of omega. Now, what is x of omega? It's a cos omega naught t. So recall that this is given by pi into delta of omega minus omega naught plus delta of omega plus omega naught. Okay. Therefore, y of omega equal to nothing but minus, what is the h of omega? You see here, h of omega is equal to minus j signum of omega. Just multiply that. So this is nothing but minus j signum minus j pi signum of omega delta of omega minus omega naught minus j pi signum of omega into delta of omega plus omega naught. Okay, but this is now what is signum? Oh, okay. So basically, omega naught is a positive number. Okay, generally frequency when we write in cos omega naught is generally a positive number. So essentially, uh, okay. So this is nothing but minus j pi signum of omega naught into delta of omega minus omega naught. Why? Because this is called a shifting property. Okay, this is like x of omega in delta of omega minus omega naught is same as x of omega naught into delta of omega minus omega naught. Okay, that is called the shifting property of a delta function. So your signum of omega becomes signum of omega naught. Similarly, for the other case, it is minus j pi signum of minus omega naught into delta of omega plus omega naught. Again, by the same property of using the shifting property for the second delta function. Now, what is signum of omega naught? It's omega naught is a constant, right? So it's a particular positive number. So this is equal to 1. Similarly, signum of minus omega naught is equal to minus 1. It's nothing but minus j pi delta of omega minus omega naught. Then you have plus, because minus into minus will cancel. So plus j pi into delta of omega minus plus omega naught. Okay, this is nothing but minus j pi, just take common, delta of omega minus omega naught minus delta omega plus omega naught. Now, can anyone tell me what is this implies? What is the inverse Fourier transform of this? What is the inverse Fourier transform of y of omega?
It's sine
Correct.
this
Correct.
thing.
It's sine omega naught t. Sine omega naught t has the Fourier transform minus j pi delta omega minus omega naught minus delta omega plus omega naught. So the output of your signal system is sine omega naught t when the input to the system is cos omega naught t when where the system is a 90 degrees phase shifter or a Hilbert transformer. Okay, so basically I will just do a sanity check. Okay, for example, if I have cos omega naught t, okay, and I pass it to minus pi by 2 phase shifter. Okay, what essentially am I doing? I should get cos omega naught t minus pi by 2. Okay, that is means you shift the phase by pi by 2, right? But what is this? Same as cos of omega naught pi by 2 minus omega naught t. Why? Because cos theta same as minus cos of minus theta. But what is this? Sin omega naught t. Correct. And this is same as what we have gotten using the convolution property also. Both are same. Is it okay? So if
Yes, sir.
I apply any x of t to a pi by 2 phase shifter, it will just shift by the phase by pi by 2. And that these phase shifters are called Hilbert transformer. Okay, fine. So this was the first question. Now this gives rise to the second question here. Okay. Let x of t be equal to cos 2 pi f naught t. Okay. Let x hat of t be the Hilbert transformer. Then the question is, find the output of the system. What is the system? So you have x of t, okay, that gets split into two branches. The upper branch goes and gets multiplied by cos 2 pi fct, where fc is some other frequency. See, remember the input is having frequency f naught, but this is fc. Both are different frequencies. But the lower branch first undergoes a Hilbert transformer, HT, Hilbert transformer. So output is a x hat of t. And then it undergoes a multiplier, sine 2 pi fct. Now both the outputs, you add them in such a way that um, your bot, I mean the top one is plus and your bottom is negative. That is, you subtract your upper path and the lower path, and then you get output y of t. So I'm asking you, if x of t is equal to cos 2 pi f naught t, what is y of t? This is a system. Okay, let's draw this.
Sir, please, could you explain this, sir?
Yeah, I'll explain it. Okay, this is basically your h of t. Okay, so you have x of t that is now passing through a very big h of t, a system, and you get the output as y of t. Okay, and I'm saying that this h of t system is implemented like this. That is, I take x of t, it goes to two branches. In the first branch, it gets multiplied by cos 2 pi f ct. In the second branch, it first goes through a Hilbert transformer. So which means the output is x hat of t, because that is what is given in the question. X hat of t is a Hilbert transform of x of t. And now this Hilbert transformer output is now getting multiplied by another signal sine 2 pi fct. So then what you happen, you subtract the top signal and the bottom signal. That is basically summation I'm writing, and plus above and minus below. And the output will be one signal y of t. I'm now asking you to find what this y of t is if x of t is equal to cos 2 pi, no, cos 2 pi f naught t.
Sir, this entire process is question, sir.
Yes. The question is, what is y of t if x of t is cos 2 pi f naught t?
Okay. And the complete diagram is also part of the question.
Yes. Yeah,
Okay, sir.
I'm
Okay.
explicitly saying that this is what the system does. H of t
Okay,
will
sir.
basically is captured by this system. Okay. So now the question is, what is the find the output? That's why I find the output of the system. Find the output y of t. Okay, let's do it step by step. It's a very good question. So let's do that. Okay. So now let's draw x of t first. Okay. So let's draw x of t. This cross. So what is the output here? Here, if it is cos 2 pi fct, I'm just redrawing the above diagram. So what is the output here after this multiplier? Yes.
Cos 2 pi f0t and cos 2 pi fct, sir. Both are multiplied.
No. Now just tell in terms of x of t. Just for a moment. In terms of x of t, let's then substitute x of t is equal to cos 2 pi f naught t. Now just say, can this just nothing but x of t into cos 2 pi fct. Okay.
Cos 2 pi fct. Yes, sir.
Just multiplication. That's all. Now what happens? You now in the bottom part you make Hilbert transformer, and this is nothing but x hat of t, and that undergoes a sign multiplication. So what is the output of this multiplier? X hat of t into sine 2 pi fct. Okay.
Yes, sir. Yes, sir.
Now both are going through an adder where the top part is plus and bottom part is negative. That is, output is y of t. So therefore your y of t is nothing but x of t into cos 2 pi fct minus x hat of t into sine 2 pi fct. Is it okay?
Yes, sir.
Now what should we find? We need, now I know what x of t is, given cos 2 pi f naught t into cos 2 pi fct. X hat I don't know, let's check, and sine 2 pi fct. But what is x hat of t? X hat of t is equal to Hilbert transform of x of t. Okay, therefore if x of t is equal to cos 2 pi f naught t, it implies x hat of t is nothing but cos 2 pi f naught t minus pi by 2, because Hilbert transform is a minus pi by 2 phase shifter. Okay, and this is nothing but sine 2 pi f naught t. Okay, therefore your y of t is equal to cos 2 pi f naught t into cos 2 pi fct minus sine 2 pi f naught t into sine 2 pi FCT. Is it okay?
Yes, sir.
Now what is this? Cos A cos B minus sin A sin B.
Yes, sir.
Cos
It
of
is.
A plus B. That is 2 pi F naught T plus 2 pi FCT. That is nothing but cos of 2 pi of F naught plus FC of T. Okay. So essentially what the system does is, if I take cos 2 pi F naught of T, that is your x of T, the system h of T, the output y of T is nothing but cos 2 pi F naught plus Fc of T. Correct? That is, if the input frequency is F naught, the output frequency is F naught plus Fc. That is, it basically converts, it up converts the frequency of your input signal. Is it okay? It basically adds some more frequency to your input signal. Such kind of systems are called up converters. Okay, they are called up converters. They up converts the frequency content of your input signal. For example, it was F naught, and you are up converted to F naught plus Fc. Of course, the system will decide what Fc you need to choose. Okay, for a you need to you can choose what Fc you want, and accordingly, system will apply that Fc. Okay, so where is it applicable? A very useful application. Application in communication systems. Okay, for example, if you have your if you want to communicate between two nodes, let's say there's a transmitter and there is a receiver, you will, let's say your message, that is the information is basically x of t. In general, you will not pass, you will not send this x of t directly through the air. You will up convert it to some other high frequency and then transmit the high frequency signal in the channel through the system. The receiver will receive the high frequency signal. It will then do a down conversion, similar to how there is a system that converts F naught to F naught plus Fc. There is similar system that converts F naught plus Fc to F naught. Okay, so the receiver will do down conversion and then it will decode what the message is. So this is a very important in each of our mobile phones. For example, we have this up converter. Okay, so that is basically this one question that illustrates the usefulness of a Hilbert transformer. Okay, next question. Are there any doubts? If you have any doubts, you can ask me. Okay. Next question. Consider a signal with maximum frequency of 60 hertz. Okay. Sampled at Fs equal to 150 hertz using a unit impulse train. Okay. The question is, what should be the cutoff frequency range of the low pass filter that can be used to recover the original signal from its sampled version. Okay, so essentially, if you what I'm asking is, if you go back to this diagram, so if you recall, what did we say? Okay, maybe I've gone too far. What did we say here? If I want to recover my actual continuous time signal from the sampled version, I need to pass it through a low pass filter. Now what I'm asking is, so this red line wherever it ends is called a cutoff frequency. I'm asking what is the range of cutoff frequency? How much cutoff frequency can change so that still I can recover my continuous time signal successfully from its sampled version. Okay. Now how does it depend? You see this picture. This is a good example. If you look at this picture, this red box can be from here to here. Do you agree? The minimum should be this much and maximum should be this much. Why should the minimum be this much? Because at least one box should be entering into my low pass window, but I should not include these two, so the maximum can only be this much. Do you agree?
Yes, sir. Yes.
That means this is the range of cutoff frequency that is admissible. Okay, this is now the question is, what is this frequency range for the given question? That is what is the question. Okay, let's go back and answer that. So solution. So something like this only. I'll just draw it. So it's given maximum frequency 60 hertz. So this is 60. This is minus 60. And I'm saying f is equal to 150. So if I have another box here, that will be separated. The midpoint of this box will be 150 hertz away, because I need to repeat this box with 150 as a period, right? So that means I need to shift this box by 150 hertz, and that will I get this. Similarly, on the right left hand side also, I need to shift by 150 hertz. That is your sampling frequency fs. Okay. Now that means this number is 150. So then you tell me what is the range? How much can the frequency range? It is from this range. This should be the cutoff frequency range. What is this range?
It's 90, sir.
It is. No, it should just not 90. It is omega fc between fc bit. It should be at least 60, but at most 90. Okay. Okay. At, at least you need to have 60 hertz so that you cover this window. At most you should go to 90 so that you don't cover these two windows. Okay, so it is between 60 to 90. So the range of frequencies that you can allow for the low pass filter to have its cutoff frequency is between 60 to 90 hertz. Okay.
60
Now
hertz is
let's
minimum hertz, minimum cutoff frequency, sir.
correct. 60 is the minimum cutoff frequency, because if you have less than that, let's say something like this, you're losing this information, right?
Okay, sir. Okay.
I need to have at least the width of the one box, because so that the entire information, this one box contains the information of the signal, right? Your Fourier transform of your original signal is one box. If I have less than that, I'm losing some information. The time domain signal will be different from the actual time domain signal. So I should at least allow this much, but I should not allow so much that these two should not come into. That's why this pink frequency represents the cutoff frequency range.
Okay, sir. Okay.
Yeah. Okay, so that is question 3. Well, let's move to question 4. Question 4 is as follows. Given, okay. So yeah, what is the minimum sampling frequency required to sample the signal x of t equal to sine 2 pi t by 2 pi t into cos 2 pi t. Okay, so basically what I'm asking is, what is the minimum sampling frequency, or what is the Nyquist rate, right? Nyquist rate is a minimum sampling frequency I can use. So I'm basically asking, what is the Nyquist rate of the signal x of t? Okay, so here you see basically what is the Nyquist rate? It says 2 times the maximum frequency, right? Essentially, what I'm asking is, what is the maximum frequency content of this signal x of t? Okay, yeah, of course it looks okay. Now, can anyone help me? Like now, do you have any idea how to proceed? What are what? How should I first? Let me simplify x of t. Like tell me how to simplify x of t first. You tell me, if can I write something like
Yes, sir.
this?
Cos
This
2.
can I write as 1 by 2 into sine 4 pi t. Can I write this
Yes, sir. Yes, sir.
by 2 pi t?
Yes,
I'm just
yes, sir.
using sine 2a is equal to 2 sine a cos a. So this
Yes, sir.
already is sine a into cos a is nothing but half of sine 2a. Now, what is this? Nothing but sine 4 pi t by 4 pi t. What is this?
1, sir. 1.
1? How?
Sin theta by theta. Sin. Oh,
No,
when
no, but I'm not
theta.
applying. I'm not applying any
Okay.
limits here, right? It is for any
Okay, sir. Okay. Okay.
arbitrary t. There's nothing but
Yes, sir.
just
Yes, yes,
sinc
yes.
of 4t,
If
correct?
it, yes, sir. Yes, yes.
Just some sinc of 4t. So basically, this x of t is nothing but sinc of 4t. That's all. So basically, now what I need to do, I need to take the Fourier transform of sinc of 4t and find out the maximum frequency content of in the Fourier transform. Now, what is the Fourier transform of sinc of 4t? As a rectangle signal, correct? Sinc of 4t is something like this. So first, 1 by 4. Okay. This sinc of 4t and its Fourier transform will be a rectangle in the frequency domain. For example, f domain, x of f will be a rectangle. But I don't know what is the amplitude. I don't know what is the this frequency content. What is the upper frequency, the maximum frequency content? Okay, this I need to find out. In fact, this, if I know this, then just 2 into that will be basically my Nyquist rate. That is the required answer, the minimum sampling frequency. Okay. Now I'm going to give you a small shortcut, okay, which is not there in many books or many
Sir,
references.
please explain this last sentence, sir.
Ah, so
After sync 40, up to that point is okay, sir. After that.
Correct, correct. So now, what is the question? The question is asking what is the minimum sampling frequency? That is 2 in Nyquist rate. Nyquist rate is nothing but 2 into maximum frequency content of that signal. Now, if I want to understand what is the maximum frequency content of sync 40, I need to take the Fourier transform, because Fourier transform measures the frequency content of any signal. Correct? I know that sync function in the Fourier, if you take the Fourier transform, it is a rectangular window. Is it correct?
Yes, sir. That's okay.
Basically, if it's a rectangular window, what is the maximum frequency? The frequency of the upper edge, this frequency. Okay, so I need to
Yes,
find
sir.
what this frequency is, and then this is my FM, and then 2 into FM is your minimum sampling frequency or the Nyquist rate. Okay.
Okay.
So essentially, now I need to find what FM is for sync 40. Okay, now
Okay,
I'm
sir.
going to give you a shortcut. It's a very handy shortcut. You can use it everywhere. Okay, it is not there in many books also. The shortcut is your, okay, so let me just draw it. Sync, let's say arbitrary AT. Okay, AT. Let's say that is the time dimensional x of t. The corresponding Fourier transform will be a box. Okay. Okay, maybe I should say A sync BT. If I take the Fourier transform, it's a rectangular function. That much I know, but I don't know what is. Let's say this is C minus C, and the amplitude is D. Okay, then basically this is a Fourier transform pair, but there is a very nice relation between A, B, C, D. Okay, this is basically the shortcut. I'm gonna wait. Let me just. Okay, then what this says is your B should be equal to 2C, and your that is the width of rectangle, and A should be equal to 2CD. That is the area of rectangle. This is the shortcut. Okay, you understand what I'm saying? The coefficient that accompanies the coefficient that multiplies sinc function, okay, is called as A, and let's say the argument beside your T is called as B. Okay, and let's say if in the Fourier domain the rectangle is from minus C to plus C with amplitude D, then these four numbers A, B, C, D are related by these quantities. Okay, what is the usefulness of this? You see, if I have sinc 4T, what is A? Equal to 1. What is B? Equal to 4. Correct? That means 2C is equal to 2C is equal to 1 and 2CD is equal to 4. I will be immediately able to tell what your C and D are. So essentially what this shortcut trick does you is, given a time domain signal, immediately you can write down what is a Fourier domain signal with the accurate values of what these frequencies are and what is the amplitude also. Okay, so now in our signal, in our problem, x of t is nothing but sinc 4t. Okay, now A sinc bt, right? Therefore, what is A? A is equal to 1. B equal to, what is B? 4. Therefore, implies your 4 is equal to 2C and 1 equal to 2 into C into D. Okay, so I have two equations, two unknowns, which means what is C is nothing but 2 and D is nothing but 1 by 4. This is a solution to these two equations. That means what does it mean? It means that your sinc, your sinc 4T in time domain has the Fourier transform. It ranges from minus 2 to 2 with amplitude of 1 by 4. X of f and f. Is it clear what I just told? I'm just saying your shortcut.
Yes, sir. Yes, sir.
Okay. Now, what does this do? Nothing but the maximum frequency content FM. Therefore, your Nyquist rate. What is Nyquist rate?
It's 4, sir.
Correct. 2FM equal to 4 Hertz. That's the answer. So the question is, what is the minimum sampling frequency required to sample the signal x of t is equal to sine 2 pi t into cos 2 pi t divided by 2 pi t is 4 Hertz. Okay. So that is basically, that was question 4. Okay, so let us do maybe one more question. Okay, let's do one more question. And then we will take a break. The next question is little simple. Okay, then let's take it. Question 5. Consider an RC circuit with R equal to 12 kilohertz, 12 kilo ohms, and capacitance equal to 59 nanofarads. Okay. Then let's say a unit step voltage is applied across RC circuit. Okay, and the question is, what is the time or rise time? It's called rise time for this RC circuit. Okay, so that is basically the time taken for voltage across the capacitor to rise from 10% to 90% of final value. Okay, yeah. So any leads?
So there is a direct formula 2.197 into RC.
Correct.
Can
That's
we
all.
apply this?
Correct. Exactly. Yeah. This question is just to ensure that we are segregating. We are just pulling out the formula we used in the class. Answer is 2.1972 RC, which is nothing but 2.1972 into R is 12 kilo ohms, that is 12 into 10 power 3, and C is 50 nanofarad, 50 into 10 power minus 9. And this is nothing but, let's say, 12.2, 19, yeah, 12.2 into 12 into 5 is 60 into 10, 600 into 10 power minus 6, which is nothing but 2. Okay, so let's do it again. I mean, let's do it properly, which is nothing but 213.2 into 10 power minus 4, which is nothing but 1.32 into 10 power minus 3. That is nothing but 1.32 milliseconds. Okay, that's all. Okay, so now what we'll do is we'll take a break at 7:17. We'll meet back again at 7:25 and maybe solve a few more problems. Okay, so let's continue. We're going to start with question 6. So consider a sinusoid of frequency 500 hertz, okay, sampled at fs equal to 1000 hertz. Okay, now let the sampled signal be filtered with an ideal low pass filter with cutoff frequency fc equal to 3000 hertz. Okay, question is, what are the output frequencies? Okay, so this is the question. Okay, so basically what I'm saying is there is a sinusoidal signal, for example, sine 2 pi ft, where f is equal to 500, and I'm sampling this at 1000 hertz. Okay, exactly equal to the Nyquist rate. Fine. Now let the sampled signal be filtered. That is, now this sampled signal I'm passing through a low pass filter of fc equal to 3000 hertz. Cutoff frequency is 3000 hertz. So I'm asking what will be the output frequency. Okay, so let's try to understand. So for example, solution. What is your actual x of t is nothing but sine 2 pi 500t. X ts of t, that is sampled signal, is nothing but sine 2 pi 500t at t equal to 1000 n. Right? Basically, basically you need to sample nts, right? So n into ts. Ts is not, sorry, n by 1000, not 1000 n by 1000. Okay. Now I am recovering the signal xr of t as xts of t convolution with h of t, where h of t is a low pass filter of fc equal to 3000 hertz. Now the question is, what are the frequency components in xr of t? Okay. So the way to do this, we need to go to the frequency domain and analyze, solve the question. Okay. So if I want to draw for maybe, okay, I will do something. Just for the sake of simplicity, I will consider cosinusoid, not just sinusoid. I will consider, means cos signal. Instead of a sine signal, I will consider cos signal. Okay. So it is all cos, not sine. Cos. Okay. Now, what is the Fourier transform of just x of t? X of omega will have components at two places, where minus 500 and plus 500. Do you agree? Maybe I'll do with f domain, not just omega, f domain. It'll
Yes,
have
sir.
two frequency components, minus 500 plus 500, with some amplitude. It'll maybe pi or whatever it is. 1 by 2, something like that. No problem. Some amplitude. Let's not worry about amplitude, because we're only, the question is to ask what are the frequencies present. We are only bothered about where are the non-zero values on the f axis, not bothered about what is the amplitude. Okay, this is my x of f. Now, what is the sampled version of x of f? Okay. X ts of f is nothing but, I need to repeat this 500, this thing, to make a periodic version of the signal x of f with what is the period? Period is equal to fs, which is equal to 1000 hertz. Okay, see the question, f is equal to 1000 hertz. Okay, so basically, what did I do? I need to basically shift this signal by 1000 hertz and keep shifting by it. Okay, Similarly, keep shifting this left hand impulse also by 1000 hertz, right and left. Okay, this also the right, this impulse keep shifting, make a periodic version on both left and right axis. Similarly, shift the left signal also on both to left and right, make a periodic version with period is equal to 1000 hertz. That will basically represent the Fourier transform of the sampled version. Now let's understand that. So now we are at minus 500 and 500. First, let us shift the right impulse. Let's shift the right impulse. So let's say, what is 500 plus 1000? I'll get 1500. Then 1500 plus another 1000, I will get 2500. 2500 plus 1000, I will get 3500, and so on. Okay. Similarly, you need to shift this pulse by to the left also by 1000. What is 500 minus 500? 500 into in the left hand 1000. It is basically, here I'll have one impulse at minus 500. Now another 1000 if I shift, I'll get at minus 1500. And another I will get at minus 2500. Is it clear? Similarly, I need to shift my left hand, I mean this impulse also. This is basically obtained by shifting the right impulse. Let's say this is basically signal 1. Now similarly, if I write XTS of F obtained only by, okay, this is only by shifting. It is also obtained only by shifting left impulse. That is, your right impulse will say as 500, but left impulse I will now concentrate. I will shift the left impulse by both left and right by 1000 units. So that will be, okay, minus 500 plus 1000 will again be at 500. So that is one. Another 1000 will give again 1500. Another 1000 will give 2500. Another 1000 will give 3500. On the left hand side, minus 500 minus 1000 will be minus 1500. Again minus 2500. Again minus 3500. Okay, this is, let's say, graph 2. Therefore, your actual XTS of F is nothing but TS XTS of F in 1 plus XTS of F in 2. Basically, linearity property of Fourier transform. So what do I get? I get basically the above signal, but amplitude will be doubled because I'm adding the same. See, these both are basically same signal. But if I add them, the amplitude will be doubled. That's the only difference. Okay, and what will be the frequency content? This will be 0. This will be 500, 1500, 2500, 3500, minus 500, minus 1500, minus 2500, minus 3500. And it
Sir,
keeps on
small
going.
doubt, sir.
Yes, yes.
Sir, except at 500 minus 500, only these, as per your explanation, only these two signals will be doubled, and all other will be threefold, sir. Because left side also adds to that, and right side also adds to that. Okay, sir. Previously,
No,
no signals are there. Okay, sir. Okay, sir. Right. Okay, sir. Thank you.
I mean,
Clear, sir. Clear.
is the confusion clear? Okay, okay, fine.
Okay, sir.
Okay, so this is basically the Fourier transform of a sampled signal. Okay, and this keeps on going on both. See, these impulses keep on going for every 1000 distances, 1000 frequency distance. Now what I need to do? I need to pass it through a low pass filter. What is the cutoff frequency of this signal? 3000 hertz. Okay, there's a cutoff frequency 3000 hertz. Now let me go back to this figure. So let me draw this figure again. Okay, F XTS of F and it keeps on going to right and left. This is minus 3500, minus 2500, minus 1500, minus 500, 500, 1500, 2500, and 3500. Now, where is so cutoff frequency is 3000. That means your low pass filter is something like this. Sorry. Is it okay? This is a cutoff frequency. FC is equal to 3000. FC is equal to 3000 minus 3000. Therefore, what will be the output of this? It will only contain minus 2500, minus 1500, minus 500. 500, 1500, 2500. That's all. It will not contain any other frequency because this low pass filter will ensure that all these impulses are rejected at the output. This is minus 2500. Maybe I'll write minus 2.5K, minus 1.5K, minus 500, 500, 1.5K, 2.5K. And this is frequency. Some, of course, you have some amplitude, no problem. But now the question doesn't ask about amplitude. Therefore, you tell me what are the output frequencies? Hertz, 1500 hertz, and 2500 hertz. Is it okay?
Okay, sir. Okay, sir. Does it mean that when it is sampled at 1000 hertz frequency, double the frequency, then only it's to be taken left side and right side also, sir, to shift that 500 hertz to
Yeah.
for every.
See this
Sir,
diagram.
voice is
Let's
not
go back
clear,
to
sir.
the start. Wait. Let's go
Okay,
back.
sir.
Are you able to see this diagram? You see, this was my
Yes, sir.
original frequency, but now it is. I'm shifting it both to left and right by period of omega s. That is Fs. I need to
Okay,
shift
sir.
it to both right and left.
Okay, at the time of sampling. Okay, sir. Okay.
Yes, the Fourier transform of the sampled signal will be the periodic version of the original signal shifted both left and right.
Okay, sir. Okay, sir. Okay, sir. Sir, another small doubt, sir. At the starting of the uh, question, sir. Last problem.
Last problem.
Starting
This question or
this
last?
this question,
Hmm.
sir. Latest,
Hmm.
sir. The T2 be taken at n by 1000, sir, instead of taking a sample frequency.
Yeah. So Fs is 1000. Therefore, Ts is nothing but 1 by 1000.
Okay, sir.
So I need to take at every 1 by 1000th second. I need to take the sample.
Okay, sir. Okay.
So if you remember, x of n is nothing but x of n ts. That's how we denote, right? I'm just writing ts as
Sir.
1 by 1000. That's all.
Okay, sir. Okay, sir.
Actually, to be very correct, here this should have been n. Only then n dependence will come on the right hand side. Okay.
Okay, sir.
Okay. That was the question number 6. Now let's move on to question number 7. Find the Nyquist rate of x of t equal to sine 400 pi t by pi t the whole square. The whole square. Oops. Sorry. Okay, just a minute. Are you able to see my screen?
Yes, sir. Now it's okay, sir.
Okay, so x of t, this is x of t equal to sine 400 pi t by pi t the whole square. This is a given signal, I'm asking you to find the Nyquist rate. That is 2 times the maximum frequency. So basically the question is, first we need to find what is the maximum frequency content in this signal. Okay, so let's do that. Let's solve first that solution. First, let's simplify this as x of t equal to sine 400 pi t by, I will multiply and divide by 400 pi t, the whole square. Okay, this is nothing but 16 into 10 power 4 into sine 400 pi t by 400 pi t whole square. This is nothing but 16 into 10 power 4 into sinc 400t. Do you agree?
Yes, sir. Yes, correct, sir.
So basically, if I have sinc, okay, now recall. If I have sinc 400t, I know how to find the Nyquist rate. How? I mean, basically use this shortcut, the previous this shortcut. Find the value of c, and then 2 times c, that is b value itself, will be equal to your Nyquist rate. But now I don't have sinc, just sinc. I have sinc square. So how to solve it? Yes, any idea how to solve for sinc square?
No, sir.
Okay, so I'll give you a hint. So consider sinc square as a sinc times another sinc. Then in the Fourier domain, it is basically convolution of 2 rectangular pulses. Do you agree? By convolution theorem of Fourier transforms?
Yes, sir. Yes, 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 yes.
Yeah, that is the way we need to go about this problem.
It will be triangle then.
Okay. Correct, exactly. It will become a triangle now. So oops, sorry. I don't know what's happening. Just a minute. Okay, so this is basically sinc square of 400t. Now let us just find for sinc. Oops, sorry. Okay, so basically you can write sinc square of 400t is nothing but sinc of 400t into sinc of 400t, or that is same as in Fourier domain, rectangle convolution another rectangle. Okay, so basically now I need to find, first let me find what is the Fourier transform inverse in Fourier transform of sinc 400t. Fourier transform of sinc 400t. Okay, what is the Fourier transform? Just the rectangle, right? And this is c minus c and d. Basically a is nothing but equal to 1 and b is equal to 400. Okay, so now just apply that formula, that is 2c must be equal to b, implies c is equal to 200, and 2cd is equal to a, implies d is equal to 1 by 400. 1 by 400? Yes, 1 by 400. A is equal to 1. But so basically your sinc square 400t is nothing but has a Fourier transform relation, a rectangle from minus 200 to plus 200, with amplitude 1 by 400, convolution another minus 200 to 200 with amplitude 1 by 400 x of f. Do you agree? Is it okay?
Yes, sir.
Now what is this sinc convolution of 2 rectangles, nothing but a triangle? Now what will be the endpoint of this? Basically endpoint of this nothing but the sum of the 2 endpoints, 200 plus another 200. That is the property of convolution. So this will become 400.
Yes, yes, yes. Yes, sir.
Similarly, you'll have a minus 400, but some amplitude
Yes,
will be some value. Let's not bother about it because the Nyquist rate only depends on what is the maximum value on the x-axis, not on maximum value of y-axis. Let it be some value, no problem. Okay. Therefore, max frequency content in x of t is what? Is fm equal to 400, correct. So what is the Nyquist rate?
Is 800, sir.
Correct. 2fm is equal to 800 hertz. Okay. So 200 to 800. So basically, this sinc square, basically it's a fine form of a sinc square, will have a Nyquist rate of 800 hertz. Okay. Now let's maybe solve one or two questions in discrete Fourier series. This was question number 7. Question number 8. Consider the periodic sequence x of n as shown below. Okay. The way it looks like, let me draw it for you. X of n and n 1 1 1 1 1, then 0 0 0 0 0, again 1 1 1, like that it keeps on. Now 0 0 0 0 0, 1 1 1 1 1, again it goes 0 0, like that it keeps on going. Okay, it's a periodic signal. Okay, so what is the basically, let's say this is 0 1 2 3 4 5 6 7 8 9 10 11 12 and so on. Similarly -1 -2 and so on. Okay, so it's basically a periodic signal with 5 ones. Sorry, it's a periodic signal with 5 ones 5 zeros, again 5 ones 5 zeros, similarly here 5 zeros 5 1. Okay, and like that this pattern keeps repeating. Okay, so it's a periodic discrete time signal. What is the period of the signal?
Sir, it's 10.
Correct.
10.
This is the period.
Yes, sir,
10.
10, sir.
It is n naught equal to 10. Okay, this is the period. Now this is okay. This is the question. Now basically the question is simple. Determine the Fourier coefficient Ck and sketch the magnitude spectrum. Determine the discrete Fourier coefficients Ck and sketch the magnitude spectrum. Okay, that is the question. Let's do the answer. Okay, so basically, let me write down. First of all, we need to write down the discrete Fourier series representation of your signal x of n. Therefore, by discrete, yes. Is there a question? Okay. By discrete Fourier series, we have x of n to be equal to basically x of n is nothing but summation k equal to 0 to n naught minus 1 into Ck into e power j k omega naught. Okay, j k omega naught n, of course. Yeah. Okay, this is basically your expression for your discrete Fourier series. Correct. Now what is omega naught? Omega naught is nothing but very simple. What is omega naught? See here, n naught is 10. So what is omega naught? 2 pi by n naught, right? Omega is 2 pi by n naught, which is nothing but 2 pi by 10, which is equal to pi by 5. So your omega, basically your omega naught is equal to pi by 5. Therefore, your discrete Fourier series takes the expression of n equal k equal to 0 to n naught minus 1 ck into e raised to j k pi by 5 correct pi by 5 n. Okay, is it okay? That is basically my expression for x of n. Now what needs to be found is ck. What is the value for ck? Because this is known already. K is basically this running index, n is this index x of n, pi by 5 is a constant. I need to find what ck is. Okay, to find ck, how do I find ck? Is nothing but 1 by n naught summation n equal to 0 to n naught minus 1 into x of n into e raised to minus j k omega naught n. Okay, but now what is the x? Okay, let me write down step by step. N naught n equal to 0 to what is n naught minus 1? 9, right? Because n naught is 10, so 0 to 9 x of n into e power minus j k omega naught is nothing but pi by 5. So into pi by 5 into n. Now if you look at x of n, it is having the value 1 from 0 to 4, but from 5 to 9 it is having the value 0. Correct? That means you can simplify this summation as 1 by n naught summation n is equal to 0 to 4 into x of n is 1 into e power minus j k pi by 5 n. Is it clear? Is
Yes,
it
sir.
clear? Okay,
Yes, sir. Yes, sir.
fine. Yeah. Now it is nothing but just summation over exponential, just geometric series, right? It's just a geometric series of 5 terms. That is, just use the formula for geometric series. N naught is nothing but 10. So 1 by 10 into, you can write, show that this is nothing but 1 by minus j k pi by 5 into 5 by 1 minus e power minus j k into pi by 5. Basically the expression for geometric series. Geometric series expansion. Okay, so that is nothing but, okay. Now what I will do is, okay, let me simplify. 1 minus e power j k pi by 1 minus e power minus j k pi by 5. Now what I will do is I will take 1 by 10 into e power minus j k pi by 2 common from in the numerator. So it becomes e power j k pi by 2 minus e power minus j k pi by 2. Similarly, in the denominator, I will take e power minus j k pi by 10 common. So I'll get e power minus j k pi by 10. Then this will be e power j k pi by 10 minus e power minus j k pi by 10. Is it okay?
Yes, sir.
Now, this basically the value for ck. Now, I'm asked to, okay, this is the first part. Find the discrete Fourier coefficient ck. Then next is determine, sketch the magnitude spectrum, that is mod of ck. Therefore, mod of ck is nothing but 1 by 10 into this mod will anyway cancel because e power j theta is mod 1. So, but you have mod of e power j k pi by 2 minus e power minus j k pi by 2 by e power j k pi by 10 minus e power minus j k pi by 10. But this is also by Euler's relation. You can show that this modulus becomes sine k pi by 2 by sine k pi by 10. Is it okay? Basically, sine theta is nothing but e power j theta minus e power j theta by 2 minus e power minus j theta by 2j. But under the modulus constraint, you can remove j also. But there's a by 2 will get cancelled. That's why it's sine k pi by 2 by sine k pi by 10. Okay. So this is basically
Okay,
the
sir.
expression for mod ck. Now I'm asked to sketch. Okay, you can basically find for different values of k. You can show that for different values of k, the curve, the magnitude spectrum will look something like this. I'm just drawing it, but you can verify. Mod ck. Maybe I'll do 0.5. Then it will be somewhere in between. Then 2 goes 0. Then goes somewhere here. Okay, 0, 1, 2, 3, 4, 5, 6, and so on. Similarly, symmetrical here also -1, -2, -3, -4, -5, and so on. Okay, so basically it's something like this. And then it goes on till basically I mean, it's supposed to be periodic, right? With until 9 it will go here. Again, 10th onwards it will go back to 0.5, because we told that Fourier series coefficients are also periodic. Okay, and goes something like this. I mean, this is how
Please
the
explain this last thing, sir.
so
Because for some
basically
time
what
your
I've drawn is I have
voice
just no problem. So what I did is I substituted for k equal to 1 here. Whatever answer came, I plotted here. For k is equal to 0, it's a 0 by 0 form. I need to apply limit, L'Hopital rule. I need to apply L'Hopital rule. Okay, and then find what C0 is. I'll get 0.5. Like this, like that, I basically found out the values for every k. And I'm just plotting them in this violet lines. This blue line is just to connect. This blue line is just to connect. I mean, it's not a line that exists. It's just to say how the points go. It is a dotted line. Okay.
Sir, for 2 what happens, sir? Sin pi,
For
sin
2.
pi 0. Okay.
See this guy. The numerator will become
It's
0.
sin pi.
That's why it has gone to 0.
Yes, sir. Yes.
At every even multiple will go to 0.
Yes, sir. Yes.
And again at 9, after 9, it will go back to 0.5 again. Again, this pattern will repeat. Why? Because we saw that discrete Fourier series also periodic with the same period and not. So this was our period till 9, this is 10. Again, from here, this same pattern will repeat. Okay?
Okay, sir. Okay. Sir, small doubt, sir. The starting of the problem, please, could you slide it down, sir? The same problem. E to the power of j pi by 2, it's 1, sir. Just move upwards.
Where this?
Move upside, sir. Move up this.
Move up. Okay.
Move the screen upside. At some point, I got stuck, sir. Next one, sir. Next, sir.
Same question or different question?
Same.
Oh, same
problem,
question.
Same question.
Okay. E power j pi by 2. Where is it coming? Here. Okay. You mean here? Hello? What is the exact doubt?
So this e to the power of j k pi by 2, it's 1, sir. But how e to the power of j k pi by 10 will be 1, sir?
No, it is not 1. Where did I say it is 1? I did not say this. This is not always. What? Sorry. I didn't hear you.
This one, sir. Ck is equal to 1 by 10. You have taken common from both numerator and denominator. Then how it will be cancelled, sir?
See, I have e power minus jk pi by 2, e power plus jk by 2. So they will cancel to give 1. Similarly,
sir.
I have e power minus.
After taking common, after this line, sir, how we get this next line?
How this became this, sir?
Yes, yes, yes.
Okay. If I take mod here, this will take a mod into this into mod. Similarly, this mod into this mod. Okay. But what is mod of any e power j theta is 1. Similarly, e power j theta mod is again 1. That's why both I ignored.
Okay, sir. Okay, sir. Right. Okay, sir. Sin square theta plus cos square theta will be 1.
Correct. Correct.
Sir.
Yes.
Thank you, sir. Thank you.
Irrespective of whether it is pi by 2 or pi by 10, doesn't matter. E power j theta mod is always equal to 1 for any theta.
Okay, sir. Okay.
Okay. I think I actually wanted to solve one more question, but unfortunately we are out of time. So what we'll do is we'll stop now.
Sir.
We'll continue our discussions on discrete Fourier analysis next week.
Okay, sir. Okay. Thank you, sir. Sir.
Yeah.
Small doubt,
yeah.
Sir.
Yeah, please.
Sir, how you